Kronecker Products. This is the matrix multiplication that unfortunately high school does not teach you because yeah, there's a good reason for why they don't teach you because like it's not that useful in algebra, I guess. But in the real world, especially in machine learning, there's a lot of applications, and we'll have a small section in the video where we'll talk about how and where this is used in quantum computing as well. Let's see. So mainly in this video, we're going to talk about what a Kronecker product is, why do we need it, why should we care as an AI engineer about what a Kronecker product is, how it helps us uh, do a lot of great approximations, and how it has some fantastic properties which normal matrix multiplication does not have, right? So, in very simple words, if you, in a normal matrix multiplication, if you have an M cross N matrix and if you have a P cross Q matrix, right, this N needs to always be equal to this P for you to be able to do a normal matrix multiplication, right? But that's not true for Kronecker products. For Kronecker products, you can have M cross N and P cross Q, and the N and P do not necessarily need to be equal all the time, right? So the basic definition of a Kronecker product is what you can see here. Every element of A will get multiplied with the entire matrix of B, and that's A Kronecker product or B, right? That's the English definition. And what happens is you end up with a matrix that is MP cross NQ in dimensions. So assuming A is M cross N and B is P cross Q, you end up with a matrix that is MN cross PQ in dimension, right? And that's pretty easy to understand why it would end up like that because since we can see every element in A multiplies with the entirety of B. So this, even though here B is just one element, it basically represents like the entire B matrix, right? Now, there are some very interesting properties to this, and we'll see how they are, but I can prove it to you through induction, right? Like we can do examples and prove why something is true. So before we do that, let's look at simple low dimensional examples and understand what's happening. So let's say we have A, and that's 2, 0, and 0, 4. I kept it 0 so that like it's easy to multiply and stuff. And B is 5, just 5, like a one row, one column matrix, right? Just one element. So A is 2 cross 2, B is 1 cross 1. And so we can clearly see here, right? Like we cannot do a normal matrix multiplication between A and B because we need these two to be same. But in a Kronecker product, that's not true. So A Kronecker B is where you take each element of A and multiply it with the entirety of B. And that's why I took a one element matrix so that it's just easy to do it. So it's basically just multiplying 5 with all the elements. So 2 gets multiplied with 5. So what happens if we had 5, 1, 3, 1, then we'll multiply 2 with the whole thing and put that here, right? Here in this case, it's just one element, so it's just easy for calculations. But yeah, so 2 multiplied by 5, and then 0 multiplied by 5, and then again 0 multiplied by 5, and 4 multiplied by 5, right? So you end up with this matrix 10, 0, 0, 20, right? So this is your A Kronecker B. So if you do an A Kronecker product B, and if you take the inverse of it, you will get this, right? Because this, when you invert this matrix, you end up with this matrix. Now, if we do A inverse just independently, if we invert this matrix, we end up with this, right? And if we do B inverse, we end up with that. Now, if we do an A inverse and then Kronecker product that with B inverse, you end up with this, which becomes this, right? And what you can see is that these two are the same. That is the first property and the most important property of Kronecker products. That is A Kronecker product B, and if you invert the whole thing, you can split the inverse between both, right? Because what happens is A Kronecker product B will be a very huge matrix, but and if you inverting that is a big task, right? Is a computationally a big task. But inverting A and inverting B individually and then doing a Kronecker product is much easier. Now, that's one property. Let's keep that in mind. Let's go to the next property. We need to understand what an outer product is, right? And we use this a lot in AI, especially in deep learning, where we are applying a chain rule to backpropagate the gradient. And we use this term outer product a lot in this context. So let's say we have A, 1, 2. It's a column vector, column matrix or vector, whatever. And B, that's 3, 4. Now, if you say outer product of A and B, what I'm basically trying to say is B multiplied by A transpose. And this is just a normal matrix multiplication, right? Like just not the Kronecker products. It's just a normal matrix multiplication. So because obviously we cannot multiply A and B directly because of the dimensionality issues, because this is, it's 2 cross 1 and the other one's 2 cross 1 as well. So you can't do that. But when you do BA transpose, you get this, which eventually becomes this 3, 4, 6, and 8, right? And that makes sense because it's 2 cross 1 multiplied by 1 cross 2. So it becomes a 2 cross 2 matrix. So Kronecker product of A and B would look like this. Each element of A gets multiplied with the entirety of B, right? So 1 gets multiplied with the entirety of B, 2 gets multiplied with the entirety of B, and you end up with this. I'm sure you can see where I'm going with this, right? These two have very similar, I mean, it's just a flattened version of the outer product. So what vec means is vectorized. Vectorized essentially means flattened. In simple words, it means flattened. So vectorized version of the outer product is basically a Kronecker product, and that's a very important property as well, right? This property is extremely useful in quantum mechanics. It's extremely useful in signal processing, and obviously in machine learning. Otherwise, we won't be talking about it. For those who are interested, you can stick around for this like next 1 minute. I'll just explain a very simple thing about like quantum mechanics. If particle A is in state, this is phi, right? For those who are familiar with quantum mechanics, they know what the state of a particle is. And let's say particle B is in state, let's say eta or whatever. Now, the combined state is a Kronecker product of the states. This is why when you say you have n qubits with two states, right? The the combined system, that is the entangled system, lives in a 2 power n dimensional space, and the complexity of the system scales in the exponent. So that's where the exponent comes from. It comes from the reason that they are a Kronecker product of each other, right? Now, again, a small detour, just a fun thing to know, I guess. Uh, Now let's get back to machine learning and let's get back to the things we are interested in and why we need to care about this Kronecker product. So 3 properties. The third one we'll get into soon, but these two are the main properties. You can remember that for now. And let's get into machine learning. Now, this is the fun part. This is the part where probably you can relate to what's happening. Let's look at a simple example where we have a single layer of a neural network. So let's say y equals WA, right? So A can be the input or A can be the activation of the previous layer. So if you're looking at a single layer, so that's the input. But if this layer belongs to a neural network, then the input is the output of the previous layer, right? So A is input or the activation output of the previous layer. W is the weight matrix the weight of the layer which we are talking about, and Y is the output, right? And in deep learning, we're always interested in how the loss changes with respect to the weight. So that's like the big challenge, right? Because we need to know how the change in the weight is going to impact the loss, and then we change the weights in the direction where the loss decreases. So if we apply, so this derivative is super important in like AI in general. That is how loss changes with respect to W, right? Now, with chain rule, we can say that dl by dw is dl by dy times dy by dw. So the rate of change of loss with respect to y multiplied by the rate of change of y with respect to w. But if we differentiate this equation, right? If we take this equation and if we do dy by dw, we get a, because dy by dw, if you do it on both sides, you get a, right? So what we come out is that dy by dw is a, and let's assume dl by dy is g, right? Because y is basically the output, and loss with respect to the output is basically a gradient. I mean, in very simple words. So uh, if we replace this A and G into this chain rule, we get this formula, right? Where the rate of change of loss with respect to your weight is your gradient multiplied by your activation output slash input, or whatever that you want to consider it as. This is obviously in not in a vectorized form. And obviously to use it in deep learning, we need it in a vectorized, in a matrix form, if you say so. Um, because obviously you can do NumPy operations and parallelize them and all that stuff, all the good stuff. So when you write this in a matrix form, this is what you get, right? You get the gradient of loss with respect to weight is G times A transpose. That is the outer product between G and A, right? That's what G A transpose means. And that's what we discussed here, right? The outer product is basically that. So this part, you might need to have some background, and I've explained and I've gone through these concepts in my previous videos. The concept you need to know is what a Hessian or what a Fisher matrix is. So I'll give you a very quick rundown of what a Fisher matrix and a Hessian is. So the Hessian is the second order derivative of the loss, right? Because your gradients are always first order, so you differentiate your gradient, your loss twice, right? Fisher matrix is the negative of the expected value of the Hessian. So that's complicated. If you know, I have a full video explaining that. You can check it out. I'll link it somewhere in the video. Yeah. But it for now, all you need to think about it is as a second order partial derivative, right? And even though Fisher is an expectation of this, it is still a second order matrix. If we have to keep it very simply, right? So these both are huge matrices. So if a layer is m cross n, both the Fisher and the Hessian are both m cross n square in dimension, right? Because it's a covariance. Here you can see it's a covariance of the gradients, and here it's a second order partial derivative of each parameter with respect to each other. So if you have n number of parameters, you have n square number of elements in a second order derivative. So if your matrix is m cross n, then you'll have an m cross n square number of elements in this matrix. In simple words, a Fisher information matrix is basically just a expectation of the gradient multiplied by its transpose, right? Now, we'll use the vectorized version because that's what we always use in deep learning, because the vectorized versions are much easier to manipulate with NumPy and parallelize and use the GPU efficiently and things like that. Basically tensor operations, right? So the Fisher information matrix is the expectation of gradient of loss multiplied by the transpose of the gradient of loss, right? So it's a second order interaction of loss gradients in very simple words, right? Because what happens is you're multiplying the gradient of loss with its transpose. So what happens is every element in this tensor gets to interact with every element in this tensor. So you end up with a second order interaction of these loss gradients. Now, one thing which we saw already is that the outer product of two things is the vectorized version of the outer product is nothing but the Kronecker product. And we proved that property in the beginning. So we'll use that here, right? Because essentially we can say that the loss is basically GA transpose because we proved that here. Now, when we put that here and then use the Kronecker product property to substitute, we end up with this, right? Each outer product gets replaced by its Kronecker product. So the transpose gets substituted by the transpose. So it's very straightforward, right? You have an outer product, we are replacing it with a Kronecker product because we have proven that it's true. And there's no assumption still here, right? All this is like mathematically very legit. The assumption is coming in the next step. But yeah, now, we'll use a third property of the Kronecker products, which I mentioned in the beginning. That is, A Kronecker B multiplied by C Kronecker D is AC Kronecker BD, right? And if you want to prove that, you can always just take smaller matrices and then just do the operation and see it for yourself that it's true. When we use that property on this equation, what happens is this A comes here and this G goes there, right? So you get AA transpose because this one is a transpose, and then you get GG transpose, right? And you can replace that with one Kronecker product operation in the middle. That's what this formula does, right? Because here you can see C comes here, B comes there, and you get AC and you get BD. Similarly, G goes there, A goes here, and you end up with this equation. So now you need to calculate the expectation of AA transpose, Kronecker product, GG transpose, right? And that's your Fisher matrix. Why do we need the Hessian? Why do we need the Fisher? I've explained all that in the previous video. I don't want to go into it, but just think of it like this. It's a second order approximation, And normally we don't use we use the first order approximation, but if we use information from the second order, you can always account for curvature, right? Your loss landscape has some form of curvature, and when you ignore the second order, you're not really considering the curvature. You're just going for a first order approximation of the loss landscape. But we want to include we want to include information from the second order approximation so that we can make more informed parameter update steps, right? Now, now is where the assumption comes in, right? So the assumption in KFAC, or Kronecker factorized approximate curvature, is that A and G are stochastically independent. So, which is not true, of course. This is not true. Like mathematically, it's not true, but that's why it's an approximation. Obviously, we are going to assume that A and G are stochastically independent from each other. That means the input that is coming in, that can be from a previous layer, or that can be the input itself. So if it's coming from a previous layer, it's probably an activation output, right? And the gradient of the layer we are talking about, are stochastically independent. This is the only assumption we make. And this assumption allows us to break this formula into two parts, right? Initially, this was one entangled matrix of whose expectation you're calculating. That is AA transpose Kronecker product with GG transpose. But now what happens is you can split this expectation. You have expectation of AA transpose, and you can Kronecker product that with the expectation of GG transpose. So from a very computer science perspective, what happens is you reduce the time complexity from O of n square m square to O of n square plus m square, right? And what happens in linear time complexity is that if you have O of n square plus O of n square, the time complexity is still considered as O of n square, right? That's just a computer science thing. I'm assuming most of you watching this video probably know about that, right? So that's just that. This approximation helps capture the most important correlations between the weights in the same layer, right? So when you do this, when you take this approximation, you do lose out on information, but you still retain the most important correlations while still using the Kronecker product. Now, in a normal SGD, what happens is you update parameters with respect to, assuming that your second order is an identity or something like that. So your theta t plus 1 is theta t minus your learning rate multiplied by your gradients, right? This is all right, but it doesn't take the curvature into account. Now, in second order, we use the H inverse or the F inverse, whichever you want to use. Fisher information and Hessians are uh, a very strange thing in machine learning. What happens is they are not the same. Obviously, that's why they are different things. But if you really look at it, at some level, they kind of represent the same thing. And especially when you're near the point of convergence, and this is something which a lot of people don't discuss, is that especially when you're in points which are near your local minima or your objective or whatever, the Hessian and the Fisher matrix are almost the same. Like they're pretty much the same thing. In second order, we use the inverse of H and F. And what happens is we precondition the gradients with the inverse of the curvature. We need to calculate the inverse of your Hessian or your Fisher. So here we saw how F leads to this, right? And we know this property that if we have to take an inverse of A Kronecker B, then we can split that as A inverse Kronecker B inverse, right? So if I had to take an inverse of F, so F is, let's just rewrite it here clean. So F is just expectation of A transpose Kronecker expectation of G transpose, right? And if we have to take an inverse of this whole thing, the property says that we can inverse them individually, right? So this multiplied by, Kronecker product of G transpose inverse. So what happens is normally you'll have to invert this big matrix. That's where the n square m square comes from, right? Because let's say this is n square and this is m square. So you have n square m square, and you need to this is of dimension n and m. So that's where you get inverting this operation becomes an n square m square operation, right? But now what happens is here we break it down into individual, you invert it individually and then do a Kronecker product. right? This helps us bring it down to n square plus m square because you're doing the inverts individually, right? You're not inverting the whole thing. You're inverting the broken down versions of it. So this helps bring down the time complexity. And the way we use h, again, I've discussed this in the previous video, is by multiplying the h inverse with your learning rate. And this scales down the learning rate accordingly, right? If you need bigger steps, it'll do that. If you need smaller steps, it'll do that. But the idea is to use the Kronecker product to reach this very simple equation where you can individually invert second order matrices and not have to invert the combined version of it, right? And that makes a huge difference in terms of compute and how we can store data and things like that. Very cool applications. KFAC, which is the one which we just looked at as to how we can, include, somehow approximate the curvature of the loss landscape. Sometimes it's shown that the KFAC way of converging, that is using the Kronecker product to approximate the curvature. It's sometimes faster than Adam in certain tasks. Not always. Sometimes Adam works better. Another thing is Kronecker-based LoRa methods, where normally in LoRa you have an A cross B, where this A is some M cross rank and B is some rank cross N, and you kind of get the M cross N when you multiply them. But recent studies have shown that a Kronecker product between A and B helps in two ways. One is you are not restricted by this anymore. You can have different dimensions. You can have a block in between, which is the third dimension, and you can preserve the rank. So substituting your weight update with a Kronecker product seems like a very, very promising option in the LoRa based research and fine tuning. Another thing is a distributed training. So in distributed training, you need to compress training states and communicate them across GPUs, right? Because all the GPUs need to keep a track of a global idea of what's happening in this training process. So this compressing and communication, so especially the compressing part is it really helps. Kronecker products really help do that because you're able to, instead of storing like let's say a matrix which of 1 trillion, you store two small matrices of 10 power 6. So 1 trillion is 10 power 12, right? So instead of storing 10 power 12, what you can do is you can save uh, uh, smaller matrices of 10 power 6 and just Kronecker product them and get the thing back, right? So you save some memory there. The most promising area of research where Kronecker products have a huge effect is Mamba. Uh, I don't know how many people are familiar with it, but Mamba and other state space models, you guys can check out the paper. It's Mamba is very, very interesting, and at some point, I do believe that research needs to focus on memory optimization because we can't just keep scaling and think that's a solution, right? So Mamba is a super, super cool example of that, and I think I've covered mostly everything I wanted to cover. But yeah, it's a very cool product. It's a very cool idea, the whole idea of Kronecker products. And normally people don't delve into this because we just talk about normal matrix multiplication. But Kronecker products have these cool properties which allows to do cool stuff. And I think it's a topic worth making a video on. But yeah, that's it from my side. Peace.